Good afternoon. Welcome to this week's PRL Colloquium. Today we have a speaker, Prof Bobby Antony from IIT Dhanbad, who is going to talk to us. And on this online mode, I invite Professor Antony. And I understand that there are several colleagues from IIT Dhanbad also joining. And so before I actually invite Professor Vijaya Sahu to introduce our speaker and conduct the proceedings, I'd like to give a broad overview of PRL. PRL is a laboratory formed in 1947 by Dr. Vikram Sarabhai, and it's under the Department of Space, Government of India, and it's what we carry out a multidisciplinary research. And right now there are seven broad areas of research, which are astronomy, astrophysics, solar physics, planetary sciences, space and atmospheric sciences, geosciences, theoretical physics, and atomic and molecular optical physics. So wherein we carry out a wide range of research, right from, as you can see, stellar systems, active galactic nuclei, to solar coronas, interplanetary magnetic fields, to the atmospheric space, aeronomy, understanding of upper atmospheric dynamics, atmospheric aerosols, and to the very broad areas of solid earth studies, aquatic terrestrial biogeochemistry. In atomic and molecular physics, we have quantum systems, wherein and astrochemistry. And theoretical physics also covers broad areas of research, quantum chromodynamics and high energy particle physics, and so on. PRL contributes to several national and international research programs, and several of your Respond program you may be aware. Many of you're most welcome to take part in these programs. And we also conduct several outreach activities periodically to expand to kindle the scientific interest in young and not so young alike. So this is the broad overview of PRL. I would really welcome you all to please contact us at my email address of my office that is given here, dnoff@PRL. And with this, I will now call upon Professor Vijaya Sahu, my colleague, to introduce Professor Bobby Antony. Vijay.
Of this year 2020. Today we have speaker Professor Bobby Antony, and to whom we call Bobby in atomic and molecular physics community, and he is one of the well-known faces in atomic molecular physics society in India. So after finishing his early studies in Kerala, he had moved to Gujarat, especially SP University. He did his PhD there from 2000 to 2005, I think. And subsequently, he moved to Massachusetts University for doing his postdoc. And after coming back, briefly he worked as a lecturer in one of the colleges in Kerala. Then he was in TI Park as a visiting fellow for some time. Then he was appointed as a lecturer, assistant professor in Indian School of Mines that time, and it is known as Indian Institute of Technology, Dhanbad, recently. And currently he is working as professor, and also he is associate dean of student activities, and also he is chairman of doctoral student committees of IIT Dhanbad. He has several awards and honors to his name, and also he has guided several students. He has been members of Indian Physical Society, Indian Society of Atomic and Molecular Physics, Indian Association of Physics Teachers, and Indian Science Congress Association, and also he is affiliated to American Chemical Society and American Physical Society. His research interests are electron-induced chemistry, positron scattering dynamics, photoionization studies. through these studies, he is trying to explain the electron correlation behavior, the dynamic behaviors within the atomic systems, as well as the interactions with the external particles like electrons, positrons, and so on, in both astronomical objects, those systems that we find, and also the experiments that are carried out in the laboratories. So he has so far published more than 110 papers in various journals. So that is quite, it's a good record. So with this brief introduction, I would like to now request Professor Antony to speak on this electron and positron scattering from molecules. Yeah, Professor Antony, please go ahead.
Thank you, Vijaya, for that introduction. That was very descriptive. Before I begin, I think I should thank PRL, especially Professor Dukharella Pallamraju, Professor Bala, Bushet, and Vijay Sahu. Especially Bala, who invited me actually to present this talk. So I will start. Okay, let me.
You can share your screen.
Okay, so your screen is shared. My screen is shared now?
Yeah, keep going.
All right. So today I'm going to talk about electron and positron scattering from molecules. Now, when Bala contacted me about 10 days before, I was, he wanted a title and abstract immediately. So this is something which I came up, because this was something which this is what we are doing right now in our group at IIT ISM Dhanbad. Then later on, when I got the email from the dean, he was mentioning that I should be more of a general character. So I just slightly changed it to looking into the progress, problems, and possibilities in electron and positron scattering from molecules. So this will be my today's topic. So these are the four sections. I'll give a brief introduction. Then I'll talk about some progress in theory, some methodologies which has been prominent nowadays, and what are the problems now we face, or the challenges we face in these lepton collisions, and also what are the possibilities for new theories to come, new people to invest money, and so on. Okay. Well, if you look at this simple picture, this is a very common picture. If you see, it's an energy spectrum, and if you look at this portion here from around 0.01 electron volt to 10,000 electron volt, there are so many processes which happens in these environments, like gaseous nebula, stellar atoms, stars, interstellar medium, planetary atmosphere, ionosphere, lamps, arc heaters, and a lot of reactions in chemistry and biology. So this is important because this is the energy range we are looking at right now. The electron and positron colliding with atoms and molecules in this energy range. So if there are molecules here, there are abundant electrons and many positrons as well, and the reactions can cause different chemistry in that environment, which can actually lead to some kind of reactions which might occur, which might be important to know. All right. So let's start with a question. Why do you need electron scattering data? Now, the idea is, I'm not going to each and every point. I'm just going to mention these points in general. We need electron data to provide a means to probe structure and behavior of molecules in material science. We need to understand many technologies like traditional light bulbs to spark plugs in cars. We need to know low temperature plasma processing, fabrication of microelectronic chips. And in this, we need details about etching and coating of material using plasmas. And if you want to model this, we need a lot of cross sections of feedstock gases. So this is a very important area which is to the industry. The next one is a fusion plasma. A lot of chemistry is happening, especially this temperatures region. If you look at the surface of the plasma reactors, the tokamak, for example, or the diverter region, the energy is within this limit, and we need to know the process, the chemistry that is happening there. The other point is laser development and modeling, and also Monte Carlo simulations of electron probe analysis, microprobe analysis, and other electron spectroscopy. We also need to know about radiation damage in biological systems. I'll come back to this later a little bit more. And also simulation of electron transporting gases. Now, this is one of the paper which came in 2016, which is given to Klaus and Mark, which basically talks about the need of electron collision data. Electron collisions with atoms, ions, molecules, and surfaces are critically important to the understanding and modeling of low temperature plasma. So this is one of the examples where I was talking about the need for electron cross-section data. Now, why do you need positron scattering? Now, basically, studying positron scattering will help to advance knowledge of basic matter-antimatter interactions. It helps in understand the fundamental science of atomic structure and anti-hydrogen. We need to model the propagation and diffusion of dosimetry in positron emission tomography scanners, which is used in clinical therapeutics. We also need to model clinical therapeutic procedures like positherapy, and also need to understand early atmospheric events. As we know that in the beginning, all the particles and antiparticles was developed. I mean, it was produced equally, but now we have developed into a particle universe with the antiparticles not in scene. So we need to know what happened to these antiparticles and at what point it has happened. And beyond that, we have a lot of positrons in the atmosphere which can create so many chemical events. We also need to know.
Bobby, can I request? Can you
Yes.
just hide that panel in the bottom?
This one.
Just press on hide here. Thanks.
Okay, sure. Thank you. So we need to know the simulation dynamics. I mean, if you want to study this giant Penelope, LEPS, and Electron, we need the cross-section data of many molecules. And in material science, positron annihilation lifetime spectroscopy and positron microscopy for depth profile, all these things are very important. And also, if you look at the nano dosimetry effects, if you want to understand that, we need to know the scattering from small molecules. And we also need cross-section data to learn about positron accumulation and positron electron experiments. This is one of the paragraphs which I took from this review of modern physics by Thalians. We live in a molecular universe, a universe where molecules are abundant and widespread, a universe with rich organic inventory, particularly in regions of star and planet formation. A universe where the formation of stars and evolution of galaxies is driven in many ways by the presence of molecules. A universe where prebiotic interstellar molecules may represent the first steps towards life. A universe where molecules can be used as a dye to trace important processes in the interstellar medium. A universe where molecules provide unique information on the physical conditions of a wide variety of regions. And a universe where molecules can work together to form such a complex species as we are in. Now, why I want to show this, because of the richness of molecular data, atomic molecular data, which is needed. And if you go back to this another paper which came in 2018, which is a census on molecules, which is found in different regions beyond our Earth's atmosphere. So this is the crust of the paper. There are about 204 individual molecular species which has been detected now by various astronomical observations. It comprises of 16 different elements, and the size, molecular size, ranging from 2 to 70 atoms. Like the hydrogen atom was detected in 1970, and then the C70, the fullerene, in 2010. And these are some of the the list of molecules. If you see, I'm just going to flash through this. This is molecules found in interstellar medium. This is in external galaxies. This is on interstellar ices. Now, obviously, the observation on interstellar ices is very difficult because of we need some background illuminating source. So only a few molecules are observed till now, which even include an alcohol. And these are the molecules in protoplanetary disk and some in exoplanetary atmosphere. And what are the methods they use? They use radio, infrared, and visible and ultraviolet astronomy. And if you look at the detection rate, you can see that there are around 5.4 molecules being detected per year. I mean, this is basically the current rate, but actually, if you look from 68, it's around 3.7 detections per year, which itself is very high. And you can see that the due to the developments in technology, you can see the number of detections have gone much higher. I mean, if you look at, it's around more than 200 in 2020. Actually, this is 18, so another 2 years have passed. All right. So, what are the progresses which we have we've seen in collision physics? Now, I'm going to talk only about the theoretical development. Unfortunately, I'm not very expert in experimental part. So I'll just discuss about what are the the progress we have been we have reached at this point in terms of collision physics. All right. Okay. So I'm sorry. Before that, I need to show a couple of slides regarding the importance of electron scattering. If you look at this paper, which is published in 2000 in Science by Leon Sanche, this is about resonant formation of DNA strand breaks by low energy between 3 to 20 electrons. So this is a very specific case of new physics being introduced by electron scattering. Now, what is happening is, if you look at this picture here, you can talk about this is the electron energy, and this is the DNA breaks. And if you look at this is the single strand breaks, and this is the double strand breaks. If you reach somewhere around 7 electron volt, you can 7.5 electron volt, you can have a single strand break. And if you go a little bit higher to around 10 electron volt, you can even have double strand breaks in DNA. This was not even considered at that time. So what we basically learned from that experiment was strand break caused by rapid decays of transient molecular resonances localized on the DNA components. And what I mean basically is, when an electron with the low energies, now I have to apologize here when I say low energies, for atomic physics, our low energies, anything below ionization energy of a target, and intermediate energy, we talk about from ionization energy to a few hundreds of electron volt, and high energy, we talk about few hundreds and to around, say, kilo electron volt or 10,000 kilowatt electron volt. So this is a low energy in terms of atomic physics, where we are looking at an electron which is going to interact with a DNA component, and you get a transient anion. This is for a short period, and what happens is molecular vibrations start onto the system, and then it breaks. So this is not a normal procedure, because this challenges the fundamental understanding that DNA damage is possible only above the onset of ionization. So the belief that you cannot have an ionization below a particular energy was wrong. And if you look at the energy range, as I said just before, it's around 10 electron volt, 12 electron volt. I mean, this is the energy of secondary electrons produced in any radiation which you use in a therapy. So it's very important to know what kind of energy you are using, and then you should know the electrons being produced, and it can damage the DNA because of those secondary electrons. Now, we can also use this electron-driven dissociation into a selective bond breakage, so like in a molecular engineering. So this is a work by Michael Allen in 2008. What he did was he used different alcohols and ethers, and then he used electron as a probe to see how this molecule breaks because of the electron-driven processes. For example, if you look at this figure, which is taken from his paper, at around, say, around 5 electron volt, if you send an electron to this diethylamine, you can break the hydrogen from the molecule, right? Or if you can send an electron with a slightly higher energy on a butylamine, you can break the hydrogen atom. Or if you send an electron with somewhere around, say, 9 electron volt, less than 9 or slightly higher, you can basically remove one ethyl group from the dimethyl ether, or you can break the hydrogen OH bond in ethanol. To make it similar, you can look at this figure here. See, this is the ion yield when you have an electron collision. This is electron energy in electron volt on x-axis, and this is the ion yield in arbitrary units. And if you look at this figure, if you have an electron somewhere on with say 6 electron volt, which I hope it around 5 electron volt, if you send that electron, you can have a OH negative, that is, this bond can be broken. But on the other hand, if you send an electron with 8 electron volt, then you can basically break the O negative. So you get an O negative ion here, and you can get an OH negative ion in this energy. So this is basically what I call the selective bond breakage. So the idea is, like, you can have the electron, and it has got an ability to cleave selective bonds in a target. This has created a new tool to control chemistry in environments like plasma processing and radiotherapy, and even electron-induced chemistry can basically play a very important role in the chemical synthesis in space as well. Okay, so this low energy processes are also very important, along with the high energies which we have seen earlier. All right, so let's look at the theoretical methodology. And before we go into that, what is the reason you need a theory to complement the experiments? See, we need a lot of data on many targets, especially in this energy range. And if you look at the experiments, it cannot handle all these processes alone, because there are a lot of difficulties when you talk about experiments for using in to study electron or positron collisions. It's very difficult to prepare and handle targets, especially when they become reactive or toxic gases, or even larger exotic species. You need to prepare it in a gaseous form, because normally all these experiments, obviously there are some experiments which studies in condenser or surface science, but mostly they have to prepare it in a gaseous form. It's very difficult to do that, especially when the molecules are quite large. So it's very difficult to handle these exotic and large molecules. And if you want to do an experiment, it's very time consuming. For example, you can think in terms of a PhD being produced. If you look at the PhD produced by an experimental group, you will see that the thesis will have 4 or 5 molecules to the max. But if you look at the theory, you will have much more than that. So that is it's obviously time consuming, and also high cost. The experimental setup has is very high cost compared to the theoretical facilities. And theory can handle many targets. So irrespective of obviously we look into the gaseous form. All other forms are computationally very difficult, and there are many approximations available which are computationally cheap. So obviously when you look at low energy scattering, it's quite taxing computationally, but high energy theories are very fast. And we have very established techniques for quality data, and also we are continuously improving by improving the approximations which is used to predict the cross sections. So what is this is just simple background on the collision theory. The foundations was paid by Massey and Moore in 1930, and later in 90s, when the computational power became higher, we had very good methods, which extensive computational methods evolved. And the other thing is, most of these calculations generally employ the Born-Oppenheimer approximation, and we'll talk about that later. But obviously, if you assume an automatic treatment of vibration levels, you can include these vibrations at different internuclear separations, and then you can get the vibrational cross sections as well. Even then, the ab initio theories are like quasi 1 and 2 electrons, and if you look at very accurate theories, it's very difficult to manage very heavy systems. We can study the atoms like helium and a few more atoms, but if you look at tungsten, for example, which have so many electrons, valence electron, and treating all these is very difficult to converge. It's not feasible at the moment. But we know that it's an important atom in the fusion reactor. Similarly, not all aspects of electron molecule scattering can be considered solved, even for the simple system like H2. So, obviously we use, but we have reached, but nevertheless, various theoretical methods have developed and evolved over the years, predicting cross sections for immediate target system with very high accuracy. So we have to accept that as well. So today I'm going to talk about, briefly on four theoretical methods which has been used. These are four topics, commonly used. One is the Rmatrix method and Schwinger multi-channel method. They are ab initio methods. Then I talk about binary encounter weather method, which is semi-classical approach used to find ionization cross-section in the intermediate range. And also I'll talk about the optical potential method, which basically we use in our group. We also use Rmatrix method, but I'm going to talk about a little more on the optical potential method, and I'll give you some sample results on which we have obtained using optical potential method. Now, the Rmatrix method was developed into an ab initio method to calculate cross sections by Burke in 1971. Later, Nobel developed this method to include Slater type orbitals, and then we could calculate electron diatomic collisions using these orbitals. And presently, not actually presently, I mean the basic Rmatrix code of presently used methods uses Gaussian type orbitals, but later there was many improvements on that, like including pseudo potential and so on. So this was introduced by Nesman in 91. So the basic idea of Rmatrix method is division of configuration space into two regions, one internal and external region, something like this. So the inner region is basically called a channel radius with some fixed radius, say 10 atomic unit. Now, obviously, this is not a fixed value, but it depends upon what kind of a molecule you are using. The idea is that the wave function has to be within this region, and this is where sometimes we have a problem with Rmatrix, where sometimes the tail of the wave functions cross over to the region, and we do not have a complete representation of the target inside. The reason, as I said, it's a problem because we need to have a complete wave function inside the target, the inner region, the channel radius, because this is where you are going to introduce the target, and we need to find out the parameters of the target, and then this is where you do the ab initio complete problem, not a scattering problem, the complete problem of the targets. So the n+1 electron system, that is n+1 means the n electrons of the target plus the electron which is incoming, is being defined within this region, and the Rmatrix is basically calculated from the quantities in this region. And then what we can do is we do a matching at the boundary, that at A with the asymptotic solution, which gives the phase shift which contains the scattering information. Okay, so this is the basic idea. We basically partition the space to solve the composite particle target system. The solution will provide scattering observables. The inner region creates the Rmatrix, which using the parameters like pole positions and boundary amplitudes, and you can get the Rmatrix as something like this. And this looks very similar to our standard Rmatrix of this form. And by solving the scattering problem by matching at the boundary, you can get the eigenphase as this relation here, where SL and PL are called the shift and penetration factors. And if you compare with the Bragg-Wigner form, this is the Bragg-Wigner form for a resonant shift, we can compare that this very similar to it, and then by comparing these two relations, we can find the resonance position and also width. And this is why very important in the Rmatrix theory, because this is how basically predict the position of the resonance, like the one which we saw in the DNA or the alcohol, where we found a certain increase in the cross section, which basically correspond to a resonant scattering. So this basically using this method, we can predict the resonant position. So if you can predict that, that will be very good for the industry as well. And the outer region we can solve for the radial vector, which will give the K matrices, and from K matrices we can find the phase shift and also the S and T matrices by using standard relations, and you can get the cross section for a particular transition using this expression here. I'm not going too much into this equations right now. And this is, sorry, this is one of the results which is published in physics reports, where you can see this is the DCS, differential cross-section of water molecule, which gives excellent results with experiments. All right. So the next method I'm going to talk about is Schwinger multi-channel method. And this is developed from Schwinger principle. The order of development is as follows. Initially, the variational principle was developed, and then it was developed into a multi-channel method for finding cross-sections, and then now it has developed into a SMC with pseudo potentials, which you can, which can even predict cross-section slightly above ionization threshold of the molecule. So, these two methods, like a Schwinger multi-channel and the Rmatrix method, are very accurate methods. But the problem is they can deal with the problems below ionization potential, because once the ionization threshold is open, there are a lot of channels which is very difficult to do it, and then these methods will crash because of the computational demands for these methods. Okay. Well, this is obviously this has advantage over Rmatrix, because it doesn't need to worry about the boundary conditions, because it's an integral method. So these boundary conditions are obeyed automatically. But the problem comes because it needs a Green's function to solve Hamiltonian, which is sometimes very difficult. It becomes complex, and it does not have any singularities, because the method itself does not have an eigenvalue at 0, and it is very useful to produce cross-section in the static plus exchange level. So it's a very common method which is being used right now. It is later extended to multi-channel scattering with polarization effects, and it can treat both closed and open channels. It can apply to various geometries, but obviously it depends upon the computational power you have and the time you have. It's a very computationally demanding method. You can do the low energy calculations. You can, what we do is, you can include valence electron only by considering zero potential, so that the core is frozen and the nuclear potential is also included in this. This is also used in Rmatrix methods. So both methods use zero potentials to, go away with the frozen electron, the core electrons. Obviously, by using these zero potentials, you can have a smoother function, and which can be expanded with much shorter bases, and it becomes easier to. But even then, there is a catch. It needs a lot of computational power to deal with cross sections and all. Next, I will talk about a little on the binary encounter method. This is a method which normally it is used for solving the ionization cross sections of molecules. This is a semi-classical approach, and it's developed from the binary encounter model, which basically talks about soft and distant or hard and close collisions. The Mott theory basically takes care of the electron-electron hard collisions, which is called the binary encounter part, which is like a billiard ball collisions. And then the Bethe theory basically talks about the soft electron-electron collisions. That's how the binary encounter Bethe comes into picture. What BED requires, is the following inputs. That is, it needs electron binding energy for each subshell. It needs a kinetic energy with bound electron momentum and masses. These are all okay. It needs occupation number, and it needs continued dipole oscillator strength for each subshell. And this is sometimes very difficult to obtain for each subshell because it may not be available. And then obviously you can calculate the oscillator strength with using many methods like Hartree-Fock method or any other wave functions, which is it's fine. But the problem is you may not be able to get the differential oscillator strength for each subshell for all the molecules. So that will be a problem. Well, so obviously, you can find cross section, for any target, but it depends upon whether you have the oscillator strength, differential oscillator strength for the subshell or not. So, well, if in case you don't have the differential oscillator strength for each subshell, then you can get it for each orbital, and you can do the calculation, and then that is the BED model where you use. It is not as accurate as BED, but it can also give relatively good cross sections, ionization cross sections. Obviously, the integral cross section. You can. It's basically you get cross section for each orbital, and then you add to get the total cross section for the target. So this is the formula used in BED, which is all these terms are defined here, where P is the incident electron energy, P is the binding energy, U is the kinetic energy, N is orbital occupation number, and break energy, and Bohr atomic radius. All these are known quantities, and you need all these to find out the cross section. This is one of the paper where they have it's reported by Huang and Kim in 1996 using this BED method, and you can see that the cross section is excellent for carbon monoxide by electron impact. Now I'll go into the optical potential method, which we use in our group. Now, the idea of optical potential is that you need to create a model, the electron or the projectile target interaction using a model potential. So this is being modeled first. Then the scattering problem is solved quantum mechanically to obtain phase shifts, and then using phase shifts you can get the cross section. So it's a very simple method, and it's a very common method which is used in different variations in different parts of the world. Okay, I'll just briefly go into the method. So the idea is to formulate an interaction potential like this. You have a static potential because this is the potential developed by the electrons on the target. You have an exchange potential because the incoming electron and the electron of the target is indistinguishable, so you need to use exchange part. And it's a polarization potential, which is common, very known from its name itself. And finally, the absorption potential, which is because this is the part which takes care of the loss of flux, incident flux, the electron or positron. And this exchange is not there in the positron scattering, which I mean the theory base is basically similar, but this will not be there for a positron because because of the obvious reasons. All right. So what we do is we solve the Schrodinger equation through partial wave analysis or any other method if you can do it. But this method clearly represented in terms of partial wave analysis. You can obtain the phase shifts in this form, where all these terms are defined, and RL is basically the radial wave function. And using the phase shift basically is the shift in the phase, which basically correspond to any change in the incoming electron, from which we can evaluate the partial and also the total cross sections. And from this partial the phase shift and also the inelasticity, we can find elastic and inelastic cross section as given by this method here. And you should remember that in this method, the vibration and rotation is not included. So your inelastic part contains all the ionization and excitation. And if there is a positronium, if it's a positron collision, you will also have a positronium formation cross section. Obviously, we are not included the annihilation part. But then by introducing a ratio, that is Q ion by Q inelastic, we can evaluate the ionization cross section, which is termed as the CSPSE method. Now, this is one of the earlier publications which we had in 2004. This is for some molecules as electron impact ionization we have studied, and then we can see that the result was very encouraging. And later we have modified this, and we have got so many results on many molecules. I'll come back to that result later. Now, if you want to include positron collision, as I said, the treatment is very similar to electrons, but we need to we need to slightly modify the method. The problem arises when you look at positron collision. You have two channels which are not there in electron, which is one is annihilation, the other one is positronium formation. And modeling this process are not trivial actually, because it's very difficult to include in the theory. Nonetheless, with some effort, we are able to put a post-Tronian channel in our calculation, and we could implement this to get positron information cross-section. However, annihilation cross-section is still a distant reality, and I think, like I said in the previous case, like vibration and all, it's very difficult. I don't think it will be very easy to do it along with the same theory to include annihilation process. This is a recent publication in 2017 where we have reported positron information and ionization of atoms and diatomic molecules by positron impact. So if you look at, we have studied carbon and its molecule, or nitrogen and its molecule, and oxygen and molecule, and we can see that reasonably good agreement was observed for positron information. Obviously, it's not, I won't say excellent, but it's reasonably good. Well, so this is a summary of what are the cross sections which we can compute using optical potential method. This is one of the reasons this method is very, very common and very powerful. What you can do is you can find differential cross section, you can find integral elastic cross section, you can find momentum transfer cross section, you can get total inelastic cross section, total ionization cross section with a little bit of semi-classical approach, and you can get the total cross section. And for positrons, we can also get positron information if you are if you can include the positronium in the channel in the calculation, and also we can find the direct ionization, which is also not there in the electron, which is basically the which is actually without the positron information in the positron pollution. Now I'll report some of the sample results which we have for gaseous targets for electron and scattering, and also I'll show you one result on condensed phase, which is a recent one. All right. So this is ionization cross section which we have obtained by electron impact. So this is by electron scattering from gaseous targets. So this is for oxygen, sorry, xenon atom. This is for nitrogen atom. This is oxygen molecule, and this is nitrogen molecule, and this is slightly bigger molecule CH3Br3. And you can see that the cross section we have obtained is excellent, and it obeys very good with previous experiments, and then in this case with BED also, and then here also we can see that BED gives we are good with experiment also, and at the low energy with the BED as well here. And obviously we have seen that the BED this is a DM-Dushmark formalism, which I have not mentioned here. This is also a semi-classical approach. And sometimes we have found that BED has a tendency to have a different peak at different molecules, and which is slightly annoying when you compare cross sections. This is a little bit bigger molecules like CF2Cl2. You can see that excellent agreement. This black line is our result, and this is for CF3Cl. You can see a very good agreement, especially at the peak region where the maximum ionization happens. At this region, you can see the result is very good. And this is a bigger molecule, which is CCl2F2. We are within the experimental errors. Experimental errors quite high, but we are okay with that. And this is another molecule. There is a C4F7N, and we can see that the result is quite encouraging here as well. This is some of the cyclic compounds which we have done. This is pyridazine, which gives our theory gives very good results here. And this is another molecule, and with either benzene and benzoic acid, and and we have compared with BEB results also, and you can see a good comparison here as well. These are some of the results obtained in our calculation for electron impact elastic cross section, and the first one is on ethanol, and you can see that the cross section is very good. and even the shape is matched, except this point slightly different. But you can see there are two experiments here, and they don't agree very well. So I'm not sure about this part. And this is for pyridamine, pyrimidine, and this is for dimethyl ether, and this is for pyrrole. You can see this is for different molecules, and it's isomers. You can see that for different isomers also you can see different results, and here also you can see the results are quite satisfactory with the experiment, and low energy we don't have any comparisons as well. This is for total cross section. This is our old work where you can see an excellent agreement for this is oxygen O, O2, O3, and O4, and in oxygen molecule we have an excellent agreement with the experiment. And this is for a bigger molecule, which is benzene. This is relatively new data where you can see that, of course there is underestimating the experimental result, but you can see the shape is quite good. The reason may be because we have not included the rotation here. So if you can see our result, the theory, we have not included the rotational cross section here, which might have some effect on the low energy, which is similar to this here as well. Here also you can see the results are quite good for chlorobenzene. This is a reasonably new data where we have done the electron collision with a liquid water, and this is the elastic mean free path, which goes. So for mean free path, we have some of the theory which we can see here. It's quite okay with two theories at low and high energies. In between there is a mismatch, and this is the inelastic mean free path, which most of them goes quite okay. And this is the ionization cross section for liquid H2O, and then we have excellent agreement with the paper by Champion et al., which you can see here. And this is the mean free path ionization for ionization. So we can see that the electron collisions, we could manage to model electron collision with molecules, with very big molecules as well, quite satisfactorily, giving reliable cross section. So which prompted us to work on positron scattering from gaseous target as well. So I'll show you some of the examples here. So this is the ionization cross section. This is the ionization cross section for hydrogen molecule, and this is the present result. You can see excellent corroboration with the experiment. So this was really encouraging for us. And then we did on carbon monoxide, which also gave very good agreement with the experiment. This is carbon dioxide. Well, methane has an issue, which we are not sure even now why this is such high, or the experiment is quite low. But if you look at both these, we can see that there is a low cross section and then it's very similar to what you see here. So obviously we are not sure about what actually causing this difference. This is in result which I already mentioned that we could find out positron information cross section, which was very difficult to include in a collision process, but we could manage that. And these are two results which are published in 17 and 20. This is for hydrogen molecule. The result is almost within the uncertainty of the experimental results, and we have very high uncertainty errors for experiments. And this is for CO2, and you can see at the peak or the plateau we have an excellent agreement, but on both sides it's varying off, which needs to be worked out. And then this is for methane, and this is for the pyrimidine, which is also quite good at low and high and somewhere in between. But here there are some problem with the cross section which we have, which we don't know exactly what is happening to it. This is some of the total cross sections, and this is for hydrogen molecule, which has a lot of experimental theoretical data exists, and then a beautiful agreement is observed here and here as well. And here it's slightly low, but you can see that there is a very good agreement in terms of shape. And this is for methane, which is also quite good. This is for hydrogen chloride, excellent agreement. OCS, we have a good agreement towards the intermediate, but then low energy have some serious issues. This is CH3I, which is okay with this total cross section, but not with Kimura's values. And this is for a pentane molecule, which is also okay at some point, but in the middle there is an issue. This is some of the DCS cross section which we have computed, and we can see that this is for pyrimidine, and you can see that an excellent result we obtained from 1 electron volt, 3 electron volt, and 10, and then 20, and so on. This is for pentane isomers. I'll just skip this. Well, I mean, I've shown you that we can really find out cross sections for intermediate to high energy using these systems by optical potential method, or you can use BEB or DM formalisms and so on. And for low energy calculation, we can have we can use Rmatrix method or SMC method and so many others, quant variation method and so on. So the problem, but that's still there are a lot of complexities. I mean, it's not that easy as I just explained. See, the targets have infinite discrete, negative energy states. So this is something which is very difficult to model. It has got infinite continuum states. I mean, the idea is that you can't include all these states when you do the calculation. You need to have some kind of approximation. You taper off some place where. So this is where the method with pseudo potential comes into picture, where we can somehow do away with the core electrons or some of the high continuum states, right? And I mean, if you look at the ionization, just after ionization, you see there are a lot of open channels, and you can see there are 3 charged particles. I mean, a minimum of 3 charged particles, and they interact via Coulomb potentials. So how do you model that? And it becomes even more complex when more electrons are involved in very atoms, like as I said, tungsten and so on. So the molecules, if you want to study this, you need to have some kind of approximations. And the other point is, the degrees of freedom, like rotation, vibration, which you cannot directly include into your calculations. Like as I said, we use Born-Oppenheimer approximation, where you separate the nuclear and electronic motions, which means you cannot directly include vibrational motions into our problem. But we know that there is some kind of there are coupling between vibrational levels and some excitation, electronic excitations, which you will not be able to include even if you use the adiabatic technique, where we try to find out the vibrational cross sections by looking at the system at different bone lengths. So that is not actually the perfect way. Well, yeah, this is what I said. Okay, so we can include by using but the problem is we can have this kind of a coupling between vibration and electronic excitation, which we cannot include if you use Born-Oppenheimer approximation. So we need to try something else. Well, and if you look at the dynamics of many collisions, even today we can say that we are not complete. I mean obviously everyone knows that, but then these are the problems challenges we are facing, like electron positron scattering from radicals, like exotic species, very large hydrocarbon molecules, also the electron scattering from liquid phase, like we could do it for a water molecule, because the input parameters were available, someone already studied it, and then we could model that using those potentials and charge densities and so on. But what about other cases? There are a lot of cases where you need to study liquid phase, but we can't, because that our theory, there are some people who works on that, but it's in the initial stages. Also, solid like ices, or from surfaces. Like if you want to study, collision from surface, you need to from surface of ices, you need collision, and this is also a very competent theory, a part which we need to look at it. So my point here is, you can take these challenges and then use it as an opportunity for your research. We need so many data. Like if you look at the applications I mentioned earlier, we need so many reliable data, so many molecules in different phases, surfaces. We need prediction of resonances accurately. I mean, obviously, Rmatrix and SMC can predict resonances, but the problem is the accuracy of the position is very important. The calculation of dissociative electron attachment, and also the calculation of post-quantum formation cross-section. I showed you we could do that, but there are a lot of errors involved in that. It's an approximation, so we need to make it more reliable. And also inclusion of annihilation, which we could not do it for the post-quantum. Well, these are other aspects. If you look at it, inclusion of target continuum ab initio calculations, inclusion of relative stick effects, inclusion of metastable states, inclusion of vibration channel considering its coupling with electronic. Obviously it's a very difficult part, assuming that we are using Born-Oppenheimer, but can you do it in a different way? And finally, but most importantly, evaluation of uncertainty in calculations. Well, there are some developments in this stage. There are so many people working on this, including I think Vijay Sahu is working on some problems like this. Now the problem is when you are looking at approximations and how do you find out the uncertainty. Well, one way to do is you look at some benchmark calculation or benchmark experiments, look at the results and see how much you deviate from that. But the problem is when you go from, say, hydrogen molecule to, say, oxygen molecule and then methane molecule and ethanol and so on, the complexity increases and the approximation varies. So how do you exactly look at the uncertainty in those calculations? It's a very difficult task, but we need to look into this as well. So we need a lot of people working on this. Well, obviously the choices are very confusing, right? Where we should look at, okay? Because there are a lot of theories like perturbative, there are close coupling type, whether you should go for a semi-empirical type or an ab initio type, whether you look for an approximate or accurate, or a computationally cheap but faster but complex but slow, and so on. Now there is no right answer here. It depends upon what is your goal, right? What you are looking at. Is your target very complex or a simple one? Or what kind of energy range you are looking at? Is it intermediate energy range or a low energy range or a high energy range? Or what kind of transitions you are looking at? Or what accuracy you are looking for? How fast you need the result? So these are very important, and these questions are not easy to answer as well. It depends upon, if you're looking at an industry where, say, plasma, low temperature plasma, they're looking for cross sections. And then what is the accuracy they need? Is 5% enough? Is 10% enough? Or even less than 5% is needed? And we don't know. So, the idea is when you look at a molecule, and you need to look at where it's going to be applied, and you need to look at what kind of an uncertainty those communities looking for, and then we should look for the method and choose accordingly. Well, we need a lot of data, so we need a lot of people. So this platform I used to request, the Indian Atomic Molecular Physics community to come together. We need more theoreticians to look on so many systems like that. And there are so many people working on this area as well. I don't want to name anyone because I might miss many of the theoreticians. But still, we need a lot of people working on a lot of these problems. Welcome aboard. So before I finish, I think I should thank my team, Rehla, Dhanoj, Biplab, Jasprit, Pankaj, Shivam, they all passed out PhD students, but I have taken some data from their work, so I need to mention here. Nafis, Paresh, Nidhi, Himani, Iravati, they are my present PhD students, and I've taken data from them as well, and Priyanka, Ingrid, and Kritika are my UG, PG students. I should also thank the administrative and financial support from my institute and also project that is a CRB and ISRO response. And thank you all. Thank you for listening to this and watching my small presentation. Thank you very much.
Yeah, thank you, Bobby. It was a wonderful talk. Explaining atomic and molecular theory to non-experts are a little difficult, but you put it in a very simple word, so that is quite nice. I'm expecting there will be some questions. Let us see. I didn't see any questions, so maybe just finish it clearly. Let us see, because there is a time lag between YouTube stream live and here the presentation here. So probably somebody is typing some questions. Yeah, so there is a comment and also question. So nice talk. Can you please read the difference of electron and photon interaction of same energy?
Well, yes. I mean, I think I just mentioned it very briefly. I mean, both electron and positrons. When you look at the interaction, okay. So when you look at the interaction between electron and a molecule, you're talking about it's a the problem is you have an electron which is a negative charge, and the electrons on the system is negative charge, right? So, so that is one aspect, and so the change in signs in terms of potential is one aspect. When you look at the positrons, then the factor which will not affect the collision is the exchange effect, which is there in electron collision. So that exchange effect is not there in a positron collisions. Oh, I'm sorry. You talked about photon interactions. Oh, okay. My bad. All right. So, okay, photon interaction with molecules of same energy. Okay. Well, see, it's see, you basically electron when you talk about electron collisions, in terms of theoretically, it has got a the energy because of its mass, and you need to look into the energy of the photons. Okay. Now, if you are talking about the energy, basically the interaction that can happen is very similar. You can have the excitations, you can have the ionization. Like in terms of photon, you have the photoionization, and electron, you can have the electron impact ionization. You can have all those excitations as well. Okay. So the basic idea of interaction is the transfer of energy, or so you don't need to worry much about it. But if you want to model these two separately, then it is going to be very difficult. It is entirely a new different topic, so I cannot talk that in a sentence or a couple of words.
Yeah, thanks, Bobby. Maybe some people may be typing. So in the meantime, I have a couple of questions. So if you allow me, then I can ask you. Say in the beginning, when you discussed about this matter-antimatter interaction, okay, so that is why, like today we see the matter, dominated universe. Basically, it is due to the CP evolution. Okay, so the kind of this matter-antimatter interaction you study to this positron molecule interactions. So what kind of physics actually you try to
I mean, if I get it correctly, you want to ask me like what kind of interaction the positron will have with the molecules. Oh,
yes. So it's just electromagnetic, and then what kind of physics out of that you are trying?
It's very interesting because when we talk about positron colliding with a system at very low energies. If you look at it, you can have the annihilation process, which is very important. Okay, because if you look at any extraterrestrial or anywhere, you have these energies, you have production of positrons as well from cosmic ray interactions, and these this annihilation can give rise to energies which will which may start a chemical reaction. Okay, so the annihilation is one of the most important process which we should look at. The another important aspect is positronium formation. What happens is towards the about 10 electron volt to about say 150 electron volt, there is a process called positronium formation where you see the both electron and positron are basically attached together. This is not exactly a resonant process. It's not a very sharp process. It's a very broad one. As you can see the cross section if you look at it. So you can see that the electron and positron as they form a bound system. Okay, so this process is also very important to learn about this scattering. And then, I mean, if you go beyond that, if you go beyond this intermediate energy, you see that the electron and positron will not have much difference in terms of cross section. You'll see that they basically merge together. The reason is initially in terms of the interaction, if you see for positrons, due to the change in sign, they cancel out. Some interactions will cancel out, and you'll see that the cross section is much lower compared to the electron.
So basically electromagnetic interactions and the way negative antiparticles behave with interact with the
yes, that's right.
That is what you are trying to prove. Okay. So from this many-body theory point of view, I just want to know that in the Rmatrix method, how much electron correlation effect you account for the target?
This is the most important part actually. I mean, it's a very good question.
So let us say if I want to compare with the CI method or something like that. So how much electron correlation effect you have?
Yeah, this is a very important question, because the problem is when we try to include more and more states, I mean, you know that the system is going to crash. I mean, we can't do that. So now what they do is even if you look at the system with a lot of electrons in the valence band, I mean, taking all the electrons also is a big problem. So what approximation what has been done is you try to froze the inner core electrons, okay, and you assume that these core electrons do not take part in the collision process. So this is an approximation you basically do. And then
so that is not my question. See, in any method, you can assume you can take frozen core. But I am talking about in terms of the excitation, single excitation, double excitation due to the correlation.
Okay.
How much
well, see, I mean, now I've seen there are some calculations which they have included, including virtual states around 1,000. Okay, which is kind of a limited. I saw a recent article where they could go. Even in SMC also, they have gone up to around 500. I've seen state, including the virtual states, by the use of the zero potential method. Okay, so yeah, I mean, they can go to a very high state, but then, as I said, I mean, these are computationally taxing problems, and if the more the states, I mean, it's going to be a lot of problems to you. Yes.
Okay, so I have more questions. I'll ask to you later, but there is a comment by Professor Marson. I just want to read that out for you. So nice review, Bobby. I would like to talk over the liquid water data. Maybe you want to discuss it later.
Okay, maybe I'll talk to him. Maybe he wanted me to talk to him. All right. Yeah.
Okay, so I have other questions like relationship to more effect, or also the astrophysical, like the interest you are mentioning from this study. But your calculations are done at of zero temperature, right? But for astrophysical data, you need to do the calculations at higher temperature.
I'm sorry, I missed. I'm sorry, Vijay. I missed some of your audio.
Okay. Please repeat. Okay, so you are trying to highlight that the applications of your calculations to the astrophysics. Okay.
Yes, one of the area. Yes.
Yeah. So those calculations, need temperature dependent, many-body methods. But your calculations are carried out with zero temperature.
Yes.
So how do you?
Yeah, well, this is an excellent point. Actually, we haven't done that yet. Actually, this is one of the point I missed it in the challenges actually. Well, it's true. I mean, the problem of studying all these interaction at different temperatures is very important because, as he's rightly pointed out, it works in a different temperature range. So we need to work that as well. Yes, true.
And most of these experiments are carried out at lab or in accelerator method. So, like this 10 kV, like experiments that you mentioned, 0.1 eV to 10 kV. So those experiments are carried out at lab or in some accelerator facility.
Well, see, you can, I think, in terms of like 1,000, 2,000, I think you can go with the lab itself. You don't need to go for an accelerator. Yes.
Okay, so it was a wonderful talk. Actually, last year we have developed a relativistic method for atoms to do this scattering cross section.
Right.
So we have published that, and I'm looking for some people who can collaborate with me, to do some calculation. Basically, I don't use my method for this scattering processes, but I have the relativistic methods which can be
Yes.
if you want to really see the relativistic effects, then you can use that.
Yeah, sure.
So maybe now I would like to hand over the session to our Dean, Professor Raju. Then we may find out. Professor Raju, yeah.
Yes. Thank you, Professor Antony, for the nice overview. And I know it's really a tremendous amount of work that you and your group are doing. And it's really nice that I think I'm also sure that there will be a lot of colleagues of PRL who would be interested to and vice versa. So you're most welcome for this interaction. And again, on behalf of PRL and this colloquium series, I thank you again. And today, I'd like to announce the next week's colloquium, wherein we have another a researcher from PRL, and that is Dr. Vidyendu Chakravarti, who is going to give his colloquium on space weather, from anomaly to insights. And I'll request all the colleagues of PRL and also people from IIT Dhanbad who are joining us online to take part in this interdisciplinary kind of talks and colloquia. Thank you all. Thank you, Vijaya, for conducting this. Thank you, one and all. Okay.